All right, today we're putting on our detective hats for a bit of a statistical mission. Our goal? To figure out how we can prove, like really prove, that a change has actually happened. So let's just dive right in with a case.
So picture this. A company rolls out a brand new sales training program. And of course, they claim it's amazing, that it totally boosts performance. But how do you actually prove that? You've got the sales numbers from before the training, and you've got the numbers from after. So is that increase you're seeing a real change, or is it just random luck? That is the exact kind of question we are going to answer. Okay, to get to the bottom of this, first, we need to understand the kind of evidence we're dealing with. The real key here is spotting when our data isn't just two random piles of numbers, but something, well, something much more connected.
And that brings us to this big idea, what statisticians call dependent samples or matched pairs. It just means the data points come in these logical pairs. The absolute classic example, of course, is a before and after measurement on the very same person. But, it could also be a study on twins or even husbands and wives. The crucial thing to remember is that one observation is naturally linked to another. They have a partner.
Now, this is where it gets really cool. Here comes the brilliant move that makes this whole puzzle so much simpler. Instead of getting all tangled up trying to compare two different groups, we're going to perform one single elegant little trick. See, on the left, you've got your two related lists of data. All the before scores and all the after scores. Kind of looks like a mess. But watch this. On the right, we just subtract the before from the after for every single pair. And just like that, poof, we've turned it into one simple list of differences. This is the whole game changer right here. So our strategy is dead simple. Step 1, find the difference for every single pair. Step 2, you can basically forget the original data now and just focus all of your attention on that new list of differences. We've just turned a tricky two-sample problem into a much, much easier one-sample problem. And this isn't just a shortcut, it's actually more powerful. Because by looking at the change within each pair, we cancel out a ton of background noise. It makes it way easier to see if a real effect is hiding in there. So, we have our single list of differences. Now what? What tools do we actually use to analyze it? Well, this is where we open up our statistical toolkit. But first, before we start using these tools, we've got to play by the rules. We need a random sample of pairs. And that list of differences we created, it should either look kind of like a normal bell curve, or if it doesn't, we need to have at least 30 pairs to work with. And of course, we need to check for any really extreme outliers that could just throw everything off. So how do we test our claim? We need one single number that sums up all our evidence. A number that asks, how big was the average change we saw compared to the idea that there was no change at all? And it also needs to account for how many pairs we tested and how much those differences varied. That is exactly what this tool, the t-test statistic, calculates for us. But what if we want to do more than just get a yes or no answer? What if we want to estimate the true size of the change? For that, we build what's called a confidence interval. This formula gives us a range of believable values for what the true average difference is out in the real world, all based on the evidence we gathered from our sample. Okay, that's enough theory. Let's see this thing in action. We're going to take our sales training example and actually run the numbers. So here's our evidence, our case file. We looked at 15 salespeople. After we did the math, the average improvement, that's our mean difference, was 2.5 units. The standard deviation was 3.2. So here's the million-dollar question. Is this 2.5 improvement actually meaningful, or is it just statistical noise? This is where we set up our two competing ideas. First, we've got the null hypothesis, H0. Think of this as the ultimate skeptic. It says, no, the program did nothing, the true average difference is 0. Then we have the alternative hypothesis, H1. This is what we're actually trying to prove. It claims, yes, there is a real change. The true difference is not 0. We take our numbers, we plug them into that formula from a minute ago, and this is what we get. Our t-statistic is 3.0258. This one number summarizes just how strong our evidence is. And a good rule of thumb is the bigger this number is, the more our data is screaming that the skeptic, the null hypothesis, is wrong. And now for the big reveal, the p-value. The best way to think about this is If the training program was a total sham, if it did absolutely nothing, the p-value is the probability that you'd see an improvement this big just by pure dumb luck. So a tiny number like this, well, it means our result is super unlikely to just be a fluke. So to make the final call, we compare our p-value to a cutoff point we decided on beforehand called alpha, which is almost always 0.05. And look at that, our p-value is way smaller. There's a really simple rule to remember here. If the p is low, the null must go. So we make our call. We are rejecting the null hypothesis. The evidence is just too strong to ignore. We can conclude that the training program really did have an effect. The change we saw was not just some random accident. Now, before you run off and start using this awesome technique, let's talk about two really common mistakes that can lead you completely down the wrong path. First, remember that magic trick where we created one list of differences? You absolutely must use the one sample t-test on that list. Don't fall into the trap of using a test for two independent samples. And second, n is the number of pairs, not the total number of measurements. In our example, n was 15, not 30. Getting that wrong will completely mess up your results. Get those two things right, and you're golden. So there you have it. We've seen how this technique can slice right through all the noise to find a clear signal of change. And its real power is that you can use it absolutely everywhere, from testing a new diet, to a new app, to a new workout routine. The real question is, what will you use it to investigate?